Welcome back to lab. Today we're going to work on M mode, spectral Doppler, and color flow Doppler. Let's go. For a little variety, let's work on a different machine today. This is the Philips Affinity. The controls are very similar. We have the control panel, touchscreen, and monitor. On the control panel, the controls are very similar. We have freeze, acquire is print, 2D is gain, and we have the trackball. Okay, let's put the name in. Where's the keyboard? Go to the touch screen, hit patient, and there's the keyboard. It's on the touch screen. Patient data screen comes up. For patient ID, let's put in session 3. All of the machines and all of the transducers can produce M mode, 2D, spectral Doppler, and color Doppler. Here's M mode. 2D is just your regular two-dimensional imaging. Here's color flow Doppler. And this is spectral Doppler. Notice there's a focus control on the right side of the screen that you can adjust similar to the GE. You can adjust the number of focal zones and the location. Let's look at M mode first. M mode is often used for cardiac and OB. Okay, let's pick the cardiac transducer. Do adult echo. Okay, we have the sector transducer. Let's push M mode. So here's the M mode of the heart. The 2D is on top. We can move this cursor, see it on top, and pick the spot that we want to get our M mode. So here we put the M mode through the mitral valve on the 2D, and we can see the mitral valve on the M mode at the bottom. So what is M mode? M mode is motion mode. It's used to detect or evaluate motion. So what are we looking at here? Okay, this is the 2D image. This is the M mode image. Here's the 2D image and here's the cursor. We can move this cursor around any place we want. What the cursor does is you put it through one area, and then this shows the motion in that one area. Here's a left ventricle. It's contracting back and forth, and here you see it contracting here. See, this is depth. This is time. We use it on early pregnancies to demonstrate heartbeat. So here's a uterus, and here's a little gestational sac with an embryo in it. You put the cursor through, and then you can see this little motion of the heartbeat. Okay, let's examine color flow Doppler. Okay, color flow Doppler can be best demonstrated performing a carotid ultrasound. Let's go to the linear 12-4 transducer. Let's pick carotid. Place the transducer on the patient's neck, notch up. Okay, let's hit color. And here is a color Doppler of the carotid artery. Notice that it is a color box over a 2D image. When you're in color flow mode, the color switch lights up and you can change the color gain by turning the knob. Gain up. Gain down. Now we have an image of the carotid artery with the jugular vein in the same image. The jugular vein is in blue and the carotid is in red. Notice the bar in the upper right of the screen. It's telling us that flow towards the transducer is in red and flow away from the transducer is in blue. So where is the transducer? Well, of course the transducer is up here. But for the intents of the color box, think of this pointy end of where the transducer is. So the red is going towards the transducer, the blue is going away from the transducer. Look at the color box again. Notice that the top of the color box is yellow, then it goes to red, then it goes to deep blue, and it goes to light blue. The yellow color indicates that the higher velocities are yellow. High velocities towards the transducer are yellow. High velocities away from the transducer are light blue. As you can see, in the middle of the lumen, it's yellow, which is higher velocity. Towards the edges of the vessel, the velocities are slower. So, Arteries are red and veins are blue. I remember when color Doppler first came out, I went to a conference and a doctor stood up in the crowd and he said, "How does the machine know which are the arteries and which are the veins?" Good question. The answer is the machine doesn't know. You have to figure out which is the artery, which is the vein, and assign the appropriate colors. What do you do if the colors aren't right? Simply hit the invert button when you want to change the color direction. You can change the size and position of the color box using the trackball and the trackball keys. You can also change the angle of the color box using the steer control. The color box must be angled correctly to get good color imaging. You don't want to be 90 degrees to flow. That's the worst. You want to be at a sharp angle to flow. Remember, this is your transducer right here, this pointy part. Okay, what's going on with this image? Notice that in the middle of the vessel, it's blue. What's going on there? That's called aliasing. When you have aliasing in color, that means that the velocity is so high that it goes above this range and comes back below in blue. Notice that the highest velocities are in the middle of the vessel and the lower velocities are in the periphery of the vessel. So how do you eliminate aliasing? You do it by adjusting the scale. Scale is actually the pulse repetition frequency, but we'll just call it scale for now. Turn up the scale to reduce aliasing. Turn down the scale for more sensitivity, so you can image the lower velocity veins. So remember that. You heard it here. Turn up the scale to eliminate aliasing. Turn down the scale for more sensitivity. Up, eliminate aliasing. Down, more sensitivity. Okay, now how do we get spectral Doppler? First you hit the pulse wave button. Use a trackball to place your sample volume. Hit pulse wave button again. This is referred to as a duplex image. If we hit the update button, it toggles back and forth between the live color flow and the live spectral. Toggle back and forth with the update. Here's the pulse wave button, and here's the update button. And remember, you can always refer to the little guide on the bottom of the image. The whole idea is to get a good image, a good waveform, and to measure the waveform. Here you see we're measuring peak systole and end diastole velocities, and the velocities show up over here. In order to have an accurate velocity measurement, you have to have an accurate angle correction. You can change this angle, and it tells you the angle up there. Here it's 54 degrees, which is good. It's less than 60. So why is getting the angle right so important? You're probably familiar with the Doppler effect. You see a truck go by, the frequency changes. When the truck's coming towards you, the waves pile up and the frequency goes up. When the truck's going away from you, the waves get farther apart and the frequency goes down. Now with the trucks, they're emitting the sound. With the blood cells, we're bouncing sound off them. But it's the same principle. You bounce a sound wave off a red blood cell that's going towards you. The frequency, after it bounces off, is going to be higher. That change in frequency is the Doppler shift. You can call it delta frequency. Okay, so don't get nervous. Here's the formula for the Doppler shift. Use algebra to move that formula around, and you get the formula for the velocity. So the ultrasound machine figures out the difference in the frequencies, the difference between the transmitted frequency and the frequency that comes back. C is the velocity of sound in tissue. The machine knows that. The machine knows the initial frequency. The only thing the machine doesn't know is the angle. That's the thing we have to figure out. So the only thing we have to really tell the machine is the right angle, the cosine theta. Okay, so here's a rudimentary picture of what's going on in the duplex image. There's three things going on. You have your 2D image, you have your color flow image, and you have your spectral Doppler. Okay, what's this? This is your cursor. What's this little area in here? That's your sample volume. You want to have that small. This is your color bar. Your color bar is telling you that red is going towards the transducer. Remember, the transducer is on this point here. So red is towards the transducer, blue is away from the transducer. We're the ones who assign that. This is a velocity on here, so this is the waveform. Velocity towards the transducer goes up, velocity away from the transducer goes below this line. Of course, it's a carotid, so it's mostly going towards the transducer, up towards the brain. There's something missing here, the most important thing. It's the angle. So you have an angle here. We can adjust that angle. We adjust that angle to what we see. We adjust that angle to be parallel to the walls of the vessel. Remember this, we have to adjust our image by rocking back and forth of our transducer so it's 60 degrees or less. More than 60 degrees is absolutely useless. Less than 60 degrees is good. Actually, it's more accurate, but they want us to do it right around 60 degrees. Here's the angle correct knob, and you adjust that angle so it's parallel to the walls of the vessel. Okay, we got a nice image. We got 60 degrees, but what's going on here? Aliasing. Just as you can have aliasing in the color flow, you can also have it in the spectral. Note that the peak velocity tops out and it comes from the bottom. So what can we do to eliminate this aliasing? Just like in color flow, turn up the scale. Turning up the scale will eliminate the aliasing. In spectral, there's another way to eliminate aliasing. Bring down the baseline. In summary, aliasing is an artifact you have to deal with when you're using pulse wave ultrasound. Not with continuous wave, but with pulse wave. There's really 5 ways to eliminate aliasing. Number 1 is turn up the scale, which is the same as PRF, pulse repetition frequency. This GE doesn't even have a scale control. It has a PRF control. Lower the baseline. We showed that. And you can reduce your depth, the depth of your sample volume. Remember, when you reduce depth, you reduce the pulse repetition period. And pulse repetition period is the inverse of pulse repetition frequency. So when you bring your pulse repetition period down, your pulse repetition frequency goes up, and that's like turning up the scale. You could lower the frequency by going to a lower frequency transducer, or you could use continuous wave. Remember, continuous wave doesn't alias. If you remember anything today, remember your Doppler angle should be 60 degrees or less. And this is very useful. You turn up the scale to reduce aliasing, turn down the scale to increase sensitivity to low velocity, like in veins. Okay, that's it for today. We covered a lot of stuff, and I'll see you next week.